Alright, in this tutorial we're going to move away from a non-idealized fluid and look at some of the effects you get when you introduce the concept of viscosity and the drag that goes along with it. Up until this point, we've tried to deal with fluids, especially Bernoulli's equations for flow, as highly idealized. We've talked about what it means to be an ideal fluid, and we're going to formalize the assumptions here, and then we're going to actually say, well, what happens if we have this situation or that situation. The changes in the situations are going to still be very, very simple because the mathematics becomes extremely complex very, very quickly. We will see that drag that we talked about at the beginning of the year with the coffee filter lab is going to be replaced with a different type of drag. So in other words, there's two types of drag that you have to consider when you're moving through a fluid. We'll develop an equation for that and then solve a problem. I hope in class to do an example problem where we will test out this equation and see if it works in reality or approximate it fairly well. So let's start with an ideal fluid. All right, so the three main things that you want to know for a test and what it means to be an ideal fluid. First of all, it is incompressible. We mentioned this before. Okay, and that generally holds for liquids. So gases are compressible, so they're a little less than ideal. But one way of looking at what it means to be incompressible is that the density stays constant. Okay, in other words, squeezing it doesn't change the volume for a given mass, so the density would be the same. So that's not going to be an issue. Next one is that there is no viscosity. So that's an assumption we have been assuming with our fluids. So what exactly is viscosity? One way of looking at it is kind of stickiness of the substance, but I think that's misleading because some materials can be not sticky at all and be very, very viscous. So from a microscopic standpoint, or an internal, there's no internal friction between layers of the liquid. Okay, so as such, if you have a fluid with no viscosity, you don't need an external force to keep it flowing. In other words, if you spill water, it will keep flowing indefinitely because there's no internal forces to prevent the layers of liquid slipping over each other. Whereas if you spill, let's say, syrup or honey, they won't flow indefinitely because of internal forces will prevent it. So you need a constant force to keep it flowing. Lastly, an assumption we make about an ideal fluid is it involves laminar flow or steady flow as opposed to turbulence. Okay, so it's very, very difficult to model turbulent flow mathematically. We will be modeling laminar flow, and we'll also look at situations where it goes from one to the other. So I want to talk about laminar a little bit more in some of the details related to streamline. So let me define some consequences of this, and then I'll show you on the diagram here to hopefully clarify. So laminar, another way of looking at it, means that every particle that passes a given point, and that's important, a given point in the fluid will have the same speed. It does not mean every particle in the fluid has the same speed. That's a subtle distinction. In a fluid, you can have differential speed. Imagine water's flowing in a stream and it encounters a rock. The speed of the water in and near the rock is going to be different than the speed far away from the rock. That's not what laminar, that's not a contradiction of laminar. Laminar means, let's say I choose a certain spot in a fluid, right there. Every particle that passes through that spot must have the same speed. And if I choose a different spot, let's say right here, okay, the particle that passes through here might have a different speed at the green or the X versus the dot, but every particle passed through the X is going to have the same speed. Whereas if you get in this region, which is turbulent, if you have a particle pass through at one time, it might be going one speed, and then when it passes through here at another time, it might be going a very different speed. So that's what really defines turbulence. Consequent to that definition is every particle that passes a given point, doesn't matter where, must flow along the same what we call streamline. Okay, so that's a way of modeling how a particle moves. So if I take, in this case, I take a streamline, which are these dashed lines, then any particle that starts here is going to follow that blue line. And at any given point, for all particles that pass it, it's going to have the same speed. It doesn't mean it's going to be the same speed everywhere on the streamline. It just means that if I have a particle that's here, it's going to follow this line, but its speed here might be v1, its speed here might be v2, and every particle that passes at this point right here is going to be v1, and every particle passes here is going to be v2. So it can be a little bit confusing, but we want to understand what those mean. So we just have a few pictures of various flows based on the shapes of barriers that it may hit. We don't have to worry about the shape so much. We kind of know that this wing-like shape here will allow us to keep a laminar flow as seen by steady streamlines, and you get a little bit of turbulence in there. Whereas a straight up barrier like this, you get a lot of turbulence behind it in some varying degrees for different shapes there. All right, so now let's turn our attention to non-ideal fluids, or real fluids, because it's very rare that you run across something that is ideal. Okay, so the one defining characteristics that we want to look at where it makes it non-ideal is that it has viscosity, which means that any kinetic energy that you have from the moving fluid is lost to thermal energy because of that internal friction between layers. Okay, so in a crude sense, viscosity is a resistance to flow. Think of molasses. You pour it, it doesn't want to flow out by itself because the layers are constantly rubbing against each other and losing energy. And an important consequence to an object moving through viscous fluid is that there's a significant drag force. Okay, so we're going to learn that there's a drag associated with viscosity that's different than another type of drag than just moving through the fluid itself. So let's talk about viscosity a little bit more. It's not going to be a main focus in and of itself, but it will show up in other equations, especially the drag equations that we want to develop. So the symbol for viscosity is the Greek letter eta, which looks like an lowercase n. Okay, so that's a pretty good eta for me. So if you want an ETA, some books will say it's the Greek letter nu. That's not the Greek letter nu, but it's sometimes drawn like that. But for the IB, we're going to stick with eta. I'm not going to give the actual equation for viscosity because it's not necessary to know, but we do want to know the proper units. The proper units are Pascal seconds. Okay, so it's kind of an odd unit. We could break a Pascal down to a Newton per meter second and then go from there, but we'll right now leave it as a Pascal second. So let me give you two quick examples. Viscosity of water is 1 times 10 to the negative 3 Pascal seconds. And if you look at syrup, it's 1 times 10 to the 2. So the numbers themselves aren't so much important, but let's compare them. This is 5 orders of magnitude less than this. So there's a huge difference between the viscosity of those two based on the internal structure of those molecules. So this would be fairly low viscosity, whereas syrup would be fairly high viscosity, just for comparison's sake. Now, the values given are based on another parameter, and we want to be aware of this. So viscosity is very, very sensitive to temperature. Generally, as temperature goes down, viscosity goes up. Right? I've heard the expression before, someone is as slow as molasses in January. So the January is thrown in there because it's generally cold, and so it would be even extra slow molasses. All right, so with that background, now let's turn to finish up with fluid drag. Okay? Oops, wrong one. So, you may not realize this, When an object moves through a flow of fluid, you know there's going to be resistance, air resistance, drag. It turns out there are 2 distinct and independent drag forces. And we want to distinguish the two, and we're only going to model one and work with one for the curriculum. So the first one is called inertial drag. So what is inertial drag? It is the drag that you get when you push through due to pushing the fluid ahead of the object out of the way. Okay, that's an awkward way of putting it, but imagine I have some object here that's moving this way, and it's encountering air or water. Well, the air or water is in its way. In a sense, it has inertia. It doesn't want to move. So when you push it out of the way, you can make sense that it's going to push back and give you a resistance. Now, the more technical way of looking at it, and that's what this diagram is trying to show, is when the object moves through the fluid, relative to the object, the fluid is moving around it. you're going to have streamlines. And what happens is, based on how the streamlines flow, is you're going to have a zone of high pressure here and low pressure there. Okay, so you have this light zone here that's low pressure, and here it's higher. So I have a pressure differential that's that way. So if I have a pressure differential that way, that's going to be a force that way that's opposing me. Okay, and that's due to, if you will, the inertia. It has nothing to do with the stickiness, if you will, of the fluid on the object in question. So the equation for inertial drag is this one here, and we actually modeled this when we did the coffee filter lab. You've probably forgotten the details of that, but if you recall, when we did the drag force versus terminal velocity, we found that it was a square function. Okay? So it depends on the density of the fluid, the size of the object, the square of the size of the object, which we really modeled as area, but we can leave it as r squared, and then some coefficient, which was based on the shape. But that's not the one we're interested in for today. We're interested in a different type of drag called viscous drag. Okay? And that is due to tangential forces from frictional effects of the fluid. So here is a pretty decent diagram that I stole to try to explain the difference between that and inertial. So if I have some object that's moving through a fluid, and so here we see the streamlines of the fluid, is that there will be a tangential force pushing back on it due to, if you will, the stickiness of the fluid. The fluid doesn't want to flow very easily, so it's going to kind of push back. And so that's not so much because we're pushing it out of the way, it's just kind of we're slipping along it. And so a guy named Stokes, or Stoke, I'm not sure which one it is, came up with a equation, a model for this, for at least a sphere moving through the fluid. Okay, so we're going to keep our geometry simple. Even though this is not showing a sphere, that's all right. We can model what it depends on. And so I've given the equation already. It's 6 pi eta r times v. And note that I have f sub v for viscous drag. So the three parameters that matter, and we notice what distinguishes this from inertial, is it depends on the viscosity of the fluid, not its density. Certainly depends on the size of the object. That would kind of make sense. But notice in inertial, it goes by the square of the size of the object, where this is just by the first power. That's important. And then where this goes by the velocity of the sphere, the faster it goes, the more force we expect. We know that. This goes by the square of it. Most of the drag we talk about with a car applying through the air is going to be inertial, but viscous is one we want to model here. Okay, so viscous drag, unlike inertial drag, does not depend on the density of the fluid and is less influenced by the size or shape of the object. So one type of problem I want to finish with here is how do we calculate the terminal velocity of an object falling through a viscous liquid? Okay, so we're going to derive it using Stokes' law, but it's not as simple as just using this equation. We have to do a force diagram. So if I have, this is the object and it's falling through some liquid, we know that there is weight, and we know that there is a viscous drag, but we also have to consider another force. Since it's in a fluid, don't forget that there is buoyancy, right? The fluid is holding it up. So what we can say is that the viscous drag plus the buoyancy equals the weight of the object. Now we just tweak each of those terms in terms of viscosity and density and all that. So let's do each in part before we run out of time here. So this is going to be 6 pi eta times r times v. That's that. The buoyant force is going to be rho times the volume of the fluid displaced, which is the same as the volume of the object. That's the fluid times g. And this mg is going to be rho of the object times its volume times lowercase g. Okay? So if we're trying to solve for the velocity, what we're trying to solve for is this velocity term right here in our fluid drag equation. So if I move the rows to the other side, what I have is 6 pi eta r v equals v times g, rho of the object minus rho of the fluid. Okay, so we have to do one more bit of tweaking. I'll let you do that. We'll talk about that in class.